Well, thanks so much. It's really a great pleasure for me to have been invited to speak with you today, and I feel especially lucky to be able to share with you what I think is an absolutely fascinating intersection between the history of analytical instrumentation and the history of computing. So let me try to put this case as boldly as I can. Pasadena, California is one of the most important locations for the launch of the electronic computer industry in the 1950s. That should sound surprising to you. It's not commonly acknowledged. What should sound even more surprising to you is that the reason for Pasadena's importance is that it was home to two analytical instrumentation companies, the Consolidated Engineering Corporation, renamed in 1955 the Consolidated Electrodynamics Corporation, and Beckman Instruments Incorporated. In the 1950s, not only were these two companies pioneers in advanced electronic chemical instrumentation, they were also pioneers in both analog and digital electronic computers. I'll spend the remainder of my talk trying to convince you that this bold case is true by telling you two stories. My first story begins with Herbert Hoover, Jr., the oldest son of the 31st President of the United States, Herbert C. Hoover. President Hoover was known as the Great Engineer, having worked as a mining engineer after earning a geology degree from Stanford. Hoover, Jr. followed in his father's footsteps, earning his own Stanford engineering degree. After taking a Harvard MBA, Hoover, Jr. worked in radio electronics, setting up communication networks for airlines. And in 1935, he turned his interest in electronics in a new direction, petroleum exploration. That year, Hoover, Jr. created a new company, United Geophysical, in Pasadena, California. Nestled at the feet of the San Gabriel Mountains, Pasadena of the 1930s was a curious mix of resort town, residential community, and enclave of elite technology and science. Pasadena was home to Caltech and near at hand to the thriving aviation and petroleum industries in the Los Angeles Basin. Hoover's idea for United Geophysical was to develop a capability in electronic seismological instruments for use in petroleum prospecting, and then provide this capability as a service to oil firms and to governments. In this, Hoover was very closely following the lead of another firm in Texas that was doing the exact same thing. Founded in 1930 by a group of physicists, Geophysical Service Incorporated did precisely what Hoover intended to do with United Geophysical. The Texas firm had proven that foreign governments and domestic firms would pay for this electronic instrument-based service. In the 1950s, this Texas firm veered into electronic components, eventually changing its name to Texas Instruments. Very quickly after starting United Geophysical, Hoover had the idea to expand his new operation. While United Geophysical would provide seismological prospecting services, Hoover created a subsidiary company, Consolidated Engineering Corporation, in 1937 to develop new instruments for petroleum prospecting. In short order, Consolidated initiated a project to develop a mass spectrometer for this purpose under the direction of Harold Washburn, a Berkeley PhD in electrical engineering. While mass spectrometry was well established by this time, there were no commercial instruments. Each organization interested in pursuing mass spectrometry had to build their own machine. Evidently, Consolidated's concept was to use the mass spectrometer to, in essence, sniff out oil. Their plan was to use the mass spectrometer to detect telltale signs of petroleum deposits underground in the atmosphere at the surface. They would hunt trace gases that had managed to escape to the surface. While this petroleum sniffing did not pan out as hoped, Consolidated did not lose interest in the mass spectrometer. The firm pivoted to the idea of creating a commercial mass spectrometer on the premise that its abilities to identify and quantify hydrocarbons would make it of interest to big oil and related industries. Washburn and his associates readied a prototype in 1940, and by the end of 1942 had finished their first production machine, the Model 21101. It was the first commercial mass spectrometer and shipped from Pasadena to Atlantic Refining in South Philadelphia. As Consolidated readied the first 21101 for delivery, a new recruit to the company arrived in Pasadena from Iowa. The Iowan's name was Clifford Edward Barry. Barry had just been the lead engineer on one of the first electronic digital computing machines. This machine was in later years known as the Atanasoff-Berry computer, the ABC for short. Barry had graduated with a degree in electrical engineering from Iowa State in 1939 and immediately took up graduate work there in the physics department. Barry became the student of Professor John Atanasoff and his principal collaborator on the realization of an electronic digital computing machine for solving simultaneous linear equations. The necessity and challenge of solving simultaneous linear equations was well known in the physical sciences, engineering, and mathematics, interpreting complex spectra, analyzing complex electrical circuits, calculating vibration effects, and performing correlations, for example, all necessitated this particular mathematical operation. The difficulty was that the calculations required for solving these simultaneous equations were severe, taxing the most adept human calculators, even when armed with mechanical desk calculators. Atanasoff's project was to use electronic digital circuitry to create a machine that could handily compute the solutions to these simultaneous equations. In 1942, Barry had, with assistance, completed the digital computer and made significant contributions to its design. The significance of what Atanasoff and Barry had accomplished with the ABC was only evident in retrospect. While it had proven itself useful as a calculating machine for research, Barry felt that an offer to leave his graduate studies for a job working on developing new commercial mass spectrometers at Consolidated was more attractive than continuing to work on the digital computer. What Barry could not have known was that one of the most enthusiastic visitors to the Iowa lab, a physicist from Ursinus College outside Philadelphia named John Mauchly, would take inspiration and possibly ideas from the ABC into his creation of the groundbreaking ENIAC electronic digital computer between 1942 and 1946 with engineer J. Presper Eckert. The ENIAC was more of a general-purpose computer than the ABC, and Eckert and Mauchly took out broad patents on digital computers. These patents, issued in the mid-1960s, in challenges to these patents, the ABC was held as prior art, and in the early 1970s, these patents were invalidated. The lack of basic patents on digital computers really allowed the computer industry to grow in a more unfettered manner, making possible, for example, the creation of the personal computer. Returning to Barry's arrival in Pasadena in the summer of 1942, he quickly took on the task of helping to design a new mass spectrometer, essentially a new version of the 21101 with some of the acknowledged shortcomings corrected. This was the CEC Model 21102 introduced in 1945. With the new unit out and the pressures of providing mass spectrometers for wartime efforts on vital issues like the production of aviation fuels ending, Barry decided to build another electronic computer. The digital computer Barry had built in Iowa had been to surmount, as I said, the challenge of calculating solutions to simultaneous linear equations. In his work at Consolidated, he saw the users of mass spectrometers run up against this very same wall. As Barry wrote in an article in late 1945, quote, "During the war, a large number of mass spectrometers and infrared spectrophotometers were installed in petroleum refineries and research institutions. In the application of these instruments to analytical work there is the frequent necessity of solving linear, simultaneous algebraic equations, particularly in the analysis of complex hydrocarbon mixtures. As is well known, the labor involved in solving sets of this size is considerable, with the result that the present limitation on the speed of analysis is often not the obtaining of data, but rather its computation. This was the problem primarily that prompted the authors to develop the computer described in this paper," end quote. Berry's understanding of this problem of computation in mass spectrometry was deepened through his work with a mathematician at Consolidated, Sybil Rock. Rock had been at work on calculation methods using desk calculators to ease some of the calculational burden on Consolidated's mass spectrometer customers. Now, Rock worked with Berry to develop the procedures that users would follow to employ Berry's new computer. Unlike the computer in Iowa, Berry now wanted to create an electronic analog computer, not digital. Electronic digital computers perform calculations using Boolean logic by two-value operations, true, false, on, off, 0, 1. Electronic analog computers, on the other hand, perform calculations by the performance of physical models of the mathematical operations. These physical models are certain electronic circuits with values that range continuously across a domain. The analog computer creates an electronic model of the equations, and the state of the electronic circuit is the calculation's result. In this, analog calculations are dramatically fast, but relatively inflexible. It's harder to change a physical model than to program a digital computer. Nevertheless, electronic and electromechanical analog computers were more common than electronic digital computers and computing machines in 1945. So Berry quickly constructed an electronic analog computer that could solve 12 simultaneous linear equations. In essence, the computer involved an operator setting a series of 168 potentiometers by balancing an internal resistive circuit in a sequence of iterative steps to arrive at a solution. As Berry explained, quote, "The computer times are only 1/4 to 1/7 the times required by a calculator, and by calculator, Berry means a person." Because, as Berry explained, of the, quote, "frequency with which simultaneous equations are encountered in engineering, in physics, and mathematics," Consolidated elected to manufacture Berry's computer as a commercial device. It was marketed as the Model 3103 analog computer in 1946. Consolidated was now one of the very few electronic computer makers in the world. With his successful work on the 21102 mass spectrometer and the 3103 analog computer, Berry turned once again to improving commercial mass spectrometers, and in 1948 completed his PhD in Iowa on physics based on experiments on Consolidated's mass spectrometers. Berry was promoted to the chief physicist at Consolidated in 1949 and led a group of engineers to develop the company's next generations of commercial mass spectrometers. In 1953, Berry's organization launched the CEC 21103C, which became a very notable commercial success, and Berry was promoted again to Assistant Director of Research. While Berry continued to work on new commercial mass spectrometers, his analog computer opened up a new space of possibility for Consolidated as a producer of commercial computers. After several years of producing Berry's analog computer and providing Sybil Rock's materials on its use, Consolidated and the rest of the technical community saw the electronic digital computer industry really begin with the delivery of the first UNIVAC computers in 1951 by Remington Rand. Remington Rand had recently acquired the company started by Mauchly and Eckert after their creation of the ENIAC, which aimed to commercialize the general-purpose digital computer. The leadership of Consolidated began to eye an expansion into digital computing in 1951. Sybil Rock conducted a survey of Consolidated's customers to plumb their potential interest in acquiring a digital computer that could interpret the data from their mass spectrometers as well as perform other calculations and information processing tasks. Rock and her colleagues learned that there was a general demand for the digital computer as a mathematical instrument for scientists and engineers, and also for the automation of finance and accounting tasks in business. The founding president of Consolidated, Philip Fogg, considered Rock's report. Fogg's background was well suited to considering the business implications of rock survey. Fogg was a Harvard MBA who had taught economics at Caltech for 16 years before advising Hoover on the creation of Consolidated and joining it as its leader. In light of Consolidated's roaring business in mass spectrometers, its experience with Barry's analog computer, and Sybil Rock's report, Fogg decided to attack a completely open area in the fledgling digital computer industry, smaller scale, lower cost digital computers. The only commercial digital computers on the market in 1952 were large mainframes. Remington Rand's UNIVAC cost $1 million, about $8.5 million today, as did IBM's new Model 701 digital computer. At this price, the digital computer was only accessible to government and military organizations, universities, and large corporations. Fogg decided that Consolidated would create a smaller scale digital computer that would sell for only $150,000, about $1 million today. Consolidated's computer would sell for the yearly lease price of a UNIVAC. Fogg imagined that smaller scientific and engineering organizations and companies would buy the new computer for calculation, data crunching, finance, and accounting. With guidance from one of the world's very few experts in digital computers, Harry Huskey, who worked at the National Bureau of Standards in Los Angeles, Consolidated's engineers completed a prototype of their small mainframe by the end of 1953 and secured several orders for production units from Caltech's Jet Propulsion Laboratory, the National Bureau of Standards, Saucony Vacuum Oil, and Purdue University. Fogg and Consolidated's leadership saw that despite the firm's booming business in mass spectrometers, it would need greater access to capital to scale up their digital computer business. Consolidated created a new company, the ElectroData Corporation, in 1954. Stock in the new company was offered to Consolidated shareholders and the public market, while Consolidated itself purchased a third of ElectroData's stock. At the same time, ElectroData announced the small-scale mainframe as the Datatron. While Consolidated continued to witness very strong growth in the sales of their mass spectrometers, prompting them to build an entirely new, huge factory in South Pasadena to keep up with mass spec demand, what the firm saw with ElectroData was truly extraordinary. Sales and leases of the Datatron surged across 1955 into 1956. In 1955 alone, ElectroData brought in $1.5 million in sales and service revenue on the Datatron. By mid-1956, it had delivered 28 systems and had orders for another 28 on the books. ElectroData had become the third largest digital computer manufacturer after Remington Rand and IBM. The explosive success of ElectroData did not go unnoticed. In 1956, Consolidated and ElectroData, both of which Fogg directed, agreed to a takeover bid from the Burroughs Corporation. Burroughs was a leading producer of adding machines and office equipment. Its leadership eyed the purchase of ElectroData as a way to leapfrog its way into the new digital computer industry. With the Datatron, Burroughs could expand its effort in small mainframes and also build upon it to create large systems to compete with Remington Rand and IBM. In a stock swap, Burroughs bought ElectroData in 1956 for around $17 million. Burroughs went on to become a major producer of digital mainframes, one of IBM's most dogged and long-lived competitors. Clifford Berry continued his work to develop new advanced mass spectrometers at Consolidated through the 50s. In 1960, Consolidated was itself acquired by Bell and Howell, a movie equipment manufacturer turned international conglomerate with diversified holdings. Unhappy with the changes at Consolidated after the buyout, Berry left in 1963 for a job as Director of Advanced Development at the Vacuum Electronics Corporation, known as VECO, on Long Island. At the time, VECO also produced mass spectrometers and other high vacuum equipment. Sadly, Berry died that year, aged 45, likely a suicide, Barry had suffered from recurring seizures following an automobile accident in 1956. It's likely that the early death of Barry, the absorption of ElectroData into Burroughs, and the submersion of Consolidated into Bell and Howell together form the reason that the role played by this Southern California analytical instrument firm in the advent of the digital computer industry is so little known. The original individual and institutional actors disappeared, and Burroughs would have had little incentive to promote the fact that their entree into digital computing depended on the pioneering efforts of a small mass spectrometer producer from Pasadena. My second story begins with John Diebold, who, in 1952, was a 26-year-old Harvard MBA who had just published his first book titled Automation, the Advent of the Automatic Factory. Diebold's book was an expansion of a report he had co-authored at Harvard and that had been circulating among business and technical elites for a year. In his book, Diebold provided a language and a central reference for a burgeoning discussion in business, military, and technical communities in the U.S. about the transformation of industrial manufacture based on new electronic technologies coming out of the Second World War. The central image was that of the automatic factory, run by electronic computers that processed incoming data from electronic instruments and sensors that, in turn, actuated electronic controls in a fast and never-ending cycles of feedback control. As Diebold noted, the U.S. chemical industry was at the vanguard of this automation movement, having heavily invested in electronic instruments and controls for performing large-scale chemical processes. Diebold's work provided a language for Arnold O. Beckman to express his guiding strategy for the then South Pasadena-based company that he took public that year, Beckman Instruments Incorporated. Beckman was a pioneer of the modern analytical instrumentation industry, starting the firm that became Beckman Instruments in the 1930s to commercialize his electronic pH meter. Across the 1940s, Beckman's firm introduced a series of important electronic analytical instruments, from the Model DU ultraviolet spectrophotometer to infrared instruments and oxygen meters. During the war, Beckman also became a major producer of precision potentiometers. First developed by Beckman for his instruments, the potentiometer was used extensively in military and electronic systems during the war and increasingly thereafter. By 1952, Beckman had seen his instruments put to use by the chemical industry for process control and had seen the wide use of potentiometers for electronic systems and electronic controls. Beckman became seized by the fundamental connections between his firm and the automation movement and began to guide Beckman Instruments to aggressively expand into the full range of automation, electronic instruments, controls, and computers. In the spring of 1952, Beckman's deputy, a young technophilic Harvard MBA named Jack Bishop, proposed to Arnold Beckman that Beckman Instruments should jump into the electronic computing business. Beckman quickly agreed. On the basis of the firm's expertise in potentiometers and vacuum tube circuitry, Beckman and Bishop believed that the company could be a strong competitor in the new and growing market for electronic analog computers. Potentiometers and vacuum tube circuitry were the fundamental electronics at that time of electronic analog computers. Moreover, chemical engineers and researchers were already using electronic analog computers for simulations, calculations, and process control. Beckman hoped to open up a new market for analog computers by making a general-purpose, smaller-scale, lower-priced machine. The company developed plans for an analog computer that could handle a broad range of computations, but that would have the very low sales price of around $5,000, which would be about $42,000 today. At this price, the computer would be within reach of small teams or even individual users. Beckman dubbed it the EASE computer for electronic analog simulation equipment, and a team under Bishop set out to develop it. Later in 1952, Beckman also acquired a small San Francisco Bay Area company called Berkeley Scientific that specialized in digital electronic equipment, especially high-speed counters. Remarkably, between February and October 1952, Bishop's Group succeeded in building the EASE computer. The firm announced the system as, quote, the lowest-priced quality instrument in the field of analog computers, end quote, explaining that analog computers were, quote, used as an equation solver, simulator, or tester by design engineers in industrial, military, research, and educational organizations. Because most electronic computing equipment is extremely costly, this Beckman innovation, which sells for approximately $5,000 and which has broad application in many fields, is considered to be a particularly promising addition to the Beckman roster, end quote. At the end of 1952, then, Beckman was active in both analog computers and digital computing devices. At this time, there were closer to 50 than 100 total installations each of analog and digital computers in the United States, so Beckman's interest in electronic computing was prescient. Beckman's success and ambitions in automation caught the attention of the national business press. A May 1954 issue of Business Week featured a portrait of Arnold Beckman on its cover with the caption, "Automation is his market." Quote, "Things are moving so fast right now for Dr. Arnold O. Beckman," the article opened, "that even one of his own electronic computers might get out of breath keeping tally of the many things going on." This tally, the article concluded, would prominently include Beckman's sale of his 100,000th pH meter, electronic computers for automated process control, the construction of a new $2 million headquarters and factory in Fullerton, California, and the construction of a plant in Munich, Germany as the seat of his European subsidiary. The build-out was an expression of Beckman's commitment to the automation movement. As Business Week explained, quote, "Arnold Beckman's object is to construct an organization equipped to supply complete control systems for the automatic factories he sees multiplying in the future," end quote. Between 1953 and 1959, Beckman Instruments delivered over 300 electronic data processing systems, analog computers, analog and analog to digital data recorders, and process control systems. Leading the way in these systems was the EASE analog computer and also a multi-channel recorder. The multi-channel recorder used 200 Beckman potentiometers to capture incoming analog data, converting it to digital information on such media as the ubiquitous IBM punch card. The largest immediate market for these computing systems was the aerospace industry booming in the Los Angeles Basin. Engineers in the military and its suppliers used Beckman Instruments. The aerospace industry used Beckman's analog computers for flight and jet propulsion simulations, for the complex mathematical computations involved in research on guided missiles and rockets. As an internal Beckman Instruments publication put it, the EASE computer, quote, "gives push-button answers to equations, dynamics, and testing problems which normally take months or years to solve," end quote. These capabilities for fast, real-time response and data collection and conversion were also important for automated process control. Beckman Instruments systems engineers delivered an analog data recording system, a Model 111, to an ESO laboratory in 1954, where chemical engineers explored its use for the automated process control in petroleum and petrochemical manufacturing. In 1955, Beckman's engineers developed a new system around an EASE computer that allowed for closed-loop, real-time control of a wind tunnel used in missile experiments in Tennessee. With these accomplishments in sales, Beckman Instruments was recognized as a significant U.S. producer of analog computers and a leader in process control computing. While Beckman Instruments was active in analog and hybrid analog-digital computing systems well into the 60s, its place in the early history of the electronic computer industry quickly receded into obscurity. as digital computing rose to dominance across the 1960s and 1970s, taking over all of the applications for which analog computing had been successful, electronic analog computing itself diminished in importance and was eventually largely forgotten. So the obscurity of Beckman's role in the electronic computer industry went hand in hand with the fall of analog computing. So I hope you've enjoyed these two stories. I see them as acts of remembering and of looking at the early history of the computing industry from a new perspective. It's a perspective in which the analytical instrumentation industry is central. Thanks.